2 leptons. And this is the total here. This is mass of 2 muons, 2 TeV, 3 TeV, 4 TeV. This is where essentially you run out of statistics. And this is what a 3 TeV Z prime would actually look like. There's many models of different Z primes, from chi models, from string-inspired models, from all the KK resonances and so on. And depending on which one you use, you actually have different integrated luminosity that you need. This is 1, 10, 100 as a function of Z prime mass. But you see that for integrated luminosities of about 100, you cover the area somewhere between 3 and 4 TeV, depending on the actual model. Interestingly enough, this is actually a very early signal as well, which is with 0.1 inverse femtobarns, with less than a month's worth of data of an understood detector, you have a reach of 1 to 1.5 TeV for Z primes. Here, actually, the problem will be to make sure that we understand what the shape of the Drell-Yan should be. And that's where theory is going to be very important. Because you understand that in the beginning, the signal will not have this size, but it will be something put down here. It will be something like 6 events, accumulation. And the question will be whether the tail is going this way or is going up. Well, one should not get fooled by the size of these things, which are scaled to the ultimate luminosity. There is, of course, resonances also that correspond to EE out of a graviton which propagates between, say, blue-blue. The sensitivity is usually expressed on the plane that goes between the graviton mass and the coupling parameter C. This region here is the one where if this warp factor is supposed to have about the right value and not end up with yet another problem of 2 different scales. These are the various reaches, and to cut a long story short, the entire region of interest is coverable with just the standard LHC luminosity. I'll skip those. And then finally, what would be the smoking gun? The smoking gun would be to accumulate enough statistics in a Z prime search to make a spin analysis and to measure the angular distribution and to observe something like this is cosine theta star. This is with very large luminosity out of a graviton that goes to dielectrons of 1.5 TeV, and to see this distribution instead of the green that would correspond to the spin 1. This, of course, would be the first observation of a spin 2 fundamental guy. The reach for this kind of analysis is a bit higher than 1.5 TeV. This would be spectacular. It would be the first sign of something that's got to do with gravity into the world of particle physics. This particular field is evolving very fast and is attracting and has already attracted actually gigantic interest. In fact, at this point, people are turning to new issues, such as deciding when a new dilepton resonance is actually a Z prime, or it's coming out of a KK excitation, or a gauge boson, and so on. And the idea is how to disentangle it. And therefore, what you would need to do is, if you find a Z prime, you would have to go and look for a W prime, which in most, for example, in the KK case, essentially should be degenerate, because the masses are the original mass squared plus once around the loop. And the once around the loop is so large that it completely thwarts the original number. Twice around, 3 around, so essentially they're all like 1 TeV, 2 TeV, 3 TeV, if the loop momentum is, say, 1 TeV. Another example here is so-called radion phenomenology, which is, the radion is a field that there is somebody who runs in between those 2 branes. And this is a field that stabilizes a brain distance. That guy could decay into 2 Higgses. The papers are infinite in this one. In fact, creativity is really impressive. Let me finally turn to one other exciting thing you may have heard about. If indeed there is something like a TeV scale, which is relevant to the LHC, then you can also think about black hole formation in the interactions. So, there's a semi-classical argument that says that you take 2 partons and you squeeze so much energy into a very, very small area, such that you basically exceed the corresponding mass that radius has as Schwarzschild radius of the corresponding black hole mass. What that means that you're putting into a smaller radius than the corresponding black hole radius, that much energy or correspondingly mass. Now, classical relativity tells you that will automatically make a black hole because you squeezed in more in there than the corresponding radius. So if that happens, and if the scale of gravity is say 2 TeV, then what we're essentially making is little black holes. Now, what is a cross-section for something like this? This being a purely geometrical argument, it's just a surface area. So therefore, for any presumed radius, the cross-section is simply the area of a circle of that radius. So if I take m Planck to be 1 TeV, you end up with a cross-section which is 400 picobars. This is like a hertz, a black hole per second. So this is actually going to be a very high cross-section observation. Now, in fact, if it's above threshold, the LHC will be a black hole factory. It will be up to a certain factory. Yeah, it will be up to a certain minimum mass of 5 TeV, and then at that point, you will observe these spectacular events that will contain 40 jets. Because simply, this guy is completely thermic. It's completely symmetric over leptons and neutrinos and jets and so on. It will be really something different. The reach, the cross-section actually, if you look at it as the mass of the black hole, says that the ultimate is somewhere around masses of something like 8 TeV or so. This is an actual simulation of an 8 TeV one, and you don't see it here, but there's leptons coming out of the wazoo and very, very, very high energy jets everywhere. This would be a 1 TeV with n equals 6 for the extra dimensions. The interesting thing is now the argument has started over actually how a black hole would decay and what it would look like in the detector. Supposedly, this thing is going to be an S-wave guy. Remember that supposedly, once we get to a black hole which has appeared with something which is like a classical object, a black hole has no hair. So therefore, the only thing you're allowed to ascribe to it is going to be its mass, correspondingly its temperature, and angular momentum. Now, once you've gone down, what you have is basically a point radiator that's emitting S waves of particles completely equally across leptons and jets. So the first thing you would observe is a complete change of the rate at which leptons appear with respect to jets. And also, it doesn't care whether one guy is 100 GeV and the other guy is 1 GeV, because at this mass, it simply the kinematics doesn't make any difference. So the whole point is whether this is just a thermal decay of a high mass object that has a very large number of decay products, which implies a democracy along all the particles. On the other hand, you have the other school of thought that says, no, this is a completely classical picture, and in fact, this being a quantum object, you have to take quantum gravity into account, and there's no reason why it should not also decay into the Kaluza-Klein modes that propagate in the extra dimensions. So perhaps a big chunk of it will actually decay into unseen particles, or into particles that correspond to the new resonances. That would be even more spectacular. So to have 30 jets in the event, 8 leptons, you know, lots of missing energy, and in addition, you know, a resonance at 1.5 TeV because it's decayed to it. Okay, now since we've gotten to the point of science fiction, let's really push it to the end and let's talk about beyond the LHC. So people are talking about the LHC upgrade, and this is not an official plot of the expected performance of the machine. The red is the integrated luminosity, and this thing here is basically the Poisson error that you accumulate on any signal that for which you manage to maintain equal efficiency irrespective of instantaneous luminosity, if there is such a thing. Now, if you look at when you get to the 100 inverse femtobarns, by the year at worst if you assume an optimistic scenario, okay, and you look at the number of years that it takes you to half the error, and you say that by the year 2011, it will take me an extra 4 years to half any error that is of relevance, you conclude that in an optimistic scenario, by 2011, you basically reached what time can buy you. And it becomes less attractive to wait 4 more years in order to measure anything with a factor 2 more precision. So the question is if at this point you start wondering whether to upgrade so that by the time you end up in 13, 14, 15, you end up with a new threshold. What would be the motivation for something like an LHC++? First of all, obviously, a linear collider is a complementary machine to the LHC. It measures things with precision that the LHC cannot attain. It can measure fractions of branching fractions for the Higgs and so on. I will not cover that here at all. But then there was a preliminary investigation of what are the possible scenarios. One is to multiply the luminosity by yet another factor 10. That is doable as 3 factors of 2. One comes from an extra squeeze of the beam by installing new focusing quadrupoles. Another one comes from the intensity of the beam itself, and another one comes from the fact that the actual ultimate luminosity is 210 to the 34. Now, of course, imagine if there is now 20 events overlaid on each interaction, that at 10 to the 35, there will be 200 interactions overlaid on top of the single hard interaction. That will be difficult. The other possibility is to completely change the magnets. That is very costly. And to, say, double the energy. What would you gain? Well, if there is anomalies in triple gauge couplings, you would clean up on that one. Higgs rare decays, and above all, self-couplings for the Higgs, meaning double Higgs production. In extra large dimensions, there's actually an interesting side effect that you could run the machine at 14 TeV, you could run it at 28 TeV, and if you've seen extra dimensions, the ratio of cross-section actually finally gives you the number of extra dimensions, because there's 2 parameters, the radius, the size of the extra dimensions, and the number of them. Now, by having 2 points, you can actually measure the 2. News resonances, and of course, supersymmetry, and finally, the big one is strong boson-boson scattering. Remember that the SSC is a machine that would have really probed the 40 TeV era, and there would be enough statistics to look at what happens in 1 TeV WW scattering. The LHC will be breathlessly getting to the 1 TeV WW scattering with 10 or 15 events. This machine, however, could actually measure it. The reach improvement is actually quite significant, or needless to say, energy is always better than luminosity. So whether you can make detectors that can work at 10 to the 35 is a completely different thing. Just to give you a feeling for the kind of improvement that is involved, this thing here, M1/2 M0, the plane is flipped. So this is currently the ultimate LHC reach, and you see here's the mass of a gluino of 2.5 TeV. So therefore, the contour, that is for that, and quarks of 2.5 TeV. This is the ultimate LHC reach. If one was to give it 10 times the luminosity, you would get to the purple curve to about 3 TeV. So the gain is marginal, half a TeV. And then finally, if you were to double the energy and go to 28, you would get to the light blue line. So basically, doubling the energy would give you essentially double the reach in this case. So voila. People have started looking at it. I have a few plots on what could actually happen. And I want to finish with a timeline which is completely imagined. It's just a rough sketch. First physics is supposed to happen somewhere in 2008. And then soon after, as soon as we understand what the missing ET signature is and what the jet ET spectrum should be and so on, in this era is where really SUSY at 1 TeV is excluded. Exclusion is easy. Observation will be a different issue. Higgs at 200 GeV is basically completely probed by the time you get to mid-2009, 2010. One needs 10 to 20 inverse femtobarns. And then by the year 2011, incidentally, the very, very tough region with the low statistics Higgs to gamma gamma from both experiments would come in quite late with about 30 inverse femtobarns. There would be hints, but to have a clear 5 sigma signal from both experiments, it would take basically the first 2.5 years or so. And then here, one would need to really move on to higher luminosities. One would have to go from 10 to the 33 to about 10 to the 34. And by the time we accumulate 100 inverse femtobarns in this era, one, by the end of it, gets to a composite in a scale of about 40 TeV. Shutdown, some kind of upgrade, and then off we go again, supposedly, if one continues physics this way, where one sees SUSY at 3 TeV and the Z prime at 6 TeV. So to conclude, first, the machine and the experiments are on track for first collisions in 2007. There will be boring collisions, but very useful collisions in terms of commissioning the detector. That's actually the challenge that we're turning to, is the commissioning of the machine, the detectors of really unprecedented complexity and expected performance. The LHC is going to be a machine that will be absolutely decisive in finding out what the electroweak symmetry braking mechanism is. I mean, if the Higgs is Higgs or no Higgs, it will certainly tell us what is there up to 1 TeV. And it will also break new ground in exploring the TeV scale, hunting for new physics. And depending on what that new physics could be anything from easy, but it could also take the full integrated luminosity in order to disentangle what would be. But the 1 to 3 TeV particle scale, whether it's sparticles or whether it's black holes or whether it's one of these things, will be covered already with low integrated luminosity. If no unexpected bad surprises happen, well, the first thing that will happen is that this guy will complete his job and the LHC will come. And then we will discover or exclude the SM Higgs by the year 2010, discover low energy SUSY if it exists, and cover the whole mass range from 1 to 3 TeV for many, many other scenarios. And of course, having a large center of mass energy means that you have all sorts of new thresholds to play with. And then of course the question is, are there other new physics channels that could benefit from more luminosity? And that's perhaps something for LHC++. Thanks for your